I welcome you once again to another video series on real analysis. Concerning about the previous video, which is for video series 4, okay, this is what we actually treated before. And then for this example 4, it's clearly stated that we wanted to show that for a fixed for a fixed limit n, we need to um, evaluate the limit of fnm as when m tends to infinity, and at the same time for a fixed value m, for a fixed limit value m, so we need to actually take the limit of n and m, f of nm, such that n tends to infinity. So what we wanted to derive from here is that we want to confirm whether they are going to be equal to each other or not. So I can still recall that in this case we decided to find the limit of fnm such that when m tends to infinity in this case, and then we end up having this result here, this particular limit, we have it as m over m plus n. So since we are considering the limit as when m tends to infinity, I will need to divide all through by m, which is actually what I did here. So I try to divide all the terms, each of these terms, by m. So I did mean this is n tends to infinity. You divide each of this by what? By n in that case. So looking at this clearly now, it is clearly seen that after the division, we are actually left with 1 over 1 plus n over m. So by the time we insert m tends to infinity, we have n over infinity in this case. And anything over infinity, we always give you 0. So I have it as 1 over 1 plus 0 in that case. So in this case now, we have limit as when n tends to infinity of 1. And when you take the limit of a constant, you usually have the constant back. So now for the left hand side now, for the left hand side, I notice that if I solve this expression here, when I take limit as when n tends to infinity for a fixed limit value n, such that if n is outside, we have the result as 1. So from the previous video, I also said that if you take the limit as when m tends to infinity, okay, if you for a fixed limit value m, and then you decide to evaluate that of n tends to infinity, you notice that if you find the limit of when n tends to infinity of fnm, the result usually give us 0. And that is what I was okay. I think that was where I actually stopped on the previous video due to low power supply. And then looking at this now, let me quickly show that to you guys. So we are actually trying to look for a fixed value, or if we are trying to consider a fixed value, m, right? Limit as when m tends to infinity in this case. Let me try to increase this thickness. Now looking at this now, we are considering the limit as when n tends to infinity of fnm. And I think the function of fnm given to us is just m over m plus n. Now pay full at ten tion to this. Looking at this bracket now, we are only considering the limit based on n. N tends to infinity, so you are expected to divide each of dis term by n. Do you standard logic? So then I have this result here. M is fixed outside the bracket, and then inside the bracket here, since the limit is actually based on n tends to infinity, so I'm required to divide each of the term by n. Divide this also by n, and this will also be divided by n. So now in this case now, we'll be left with m tends to infinity in this case. Then if I insert n tends to infinity, wherever I see n, I want to insert infinity. That will be m over infinity, all divided by same thing as m over infinity, plus if this cancel this, I have 1. Okay, infinity over infinity is 1 in that case. So now looking at this now, anything that divides infinity, I'm not supposed to even put this again since I've inserted n tends to infinity. So m over infinity here is 0 over anything over infinity here is 0 and plus 1. So I'm left with just 0 over 1, and that is 0, right? So mind you, what we actually have as 0 is this expression here, just this expression. I have m tends to infinity. Okay, sorry, that's correct. Okay, if this is meant to be m, not n. Okay, m tends to infinity. I can still write this is allowed. Okay, but this expression I have in this bracket is actually equal to 0. That I have left. All this is equals to this, and then is equals to this, and then I have the final result as 0. So that's how it works. So I can still insert my limit as when m tends to infinity here. Do you stand that? And then to still remain here also. Now when you take the limit of a constant, you usually have the constant back. So I have it as 0. So trivially, I think that was what I got here. So now looking at this, I have the result here as 0. And then which simply implies that if you take the limit of when n tends to infinity to be fixed outside the bracket, and then you do the same thing here, they are not always equals to each other. It's just like you having that of integral of f of x dx in that case equals to when the limit is outside, okay, of when you have f of nx dx in this case. This can also be expressed as the limit is inside, okay, of as when n tends to infinity, and I think I have fnx here. This is equivalent to this, right? And then if the limits outside the integral, they are not always equal to each other. And I gave you the only condition when they can be equal. So I give that condition the last time. So that is how it works. So just take note that it is not really necessary that when you take the limit as when n tends to infinity, of when you have another limit as when m tends to infinity of a particular sequence of function. So it is not equal to the vice versa of it. When you now have m tends to infinity of limit as when n tends to infinity. When you interchange it, they are not always true. They are not always true. Okay, they are not always equals to each other. So that's how it works in that case. So our next example is that I want to try to pick a function. Okay, let's take the last because I already said I have just 5 examples here to solve. So for the fifth example now, let's say we are given a particular function, a sequence of function. Let's say we have an example. Let's say given a sequence function. Okay, let me put it that way. Given a sequence function fnx to be equal to, now in this case now you have it as sine nx all over square root of n. This is the sequence of function given to us. Now the question now says show that um show that the show that okay, let me use this word. Show that fn prime, let's say fnx, the sequence of function which is differentiable with limit, okay. Show that fnx is differentiable with limit 0. Let's put it that way. For which the derivative, when you differentiate it, fn prime of x, when you differentiate it 1 to infinity, diverges. So that's the question. Show that this sequence of function fnx is differentiable with limit 0, but for which the derivative diverges. Okay, if this f of nx is differentiable and then the limit is equals to 0, that means this f of ns converges since the limit is actually equals to 0. But when you now take the derivative of that same function, is it really necessary that, okay, since f of nx converges to 0, that is when you take the limit of this fnx and then you notice that the result is equal to 0, or the result is actually finite, that means it converges, right? Now since it converges, so what now happens? That is, what if I now decide to differentiate this function? So is it also necessary that it will also converge? No. So let's confirm. Now to prove this kind of example, okay, we start by saying, okay, we are given fnx to be equals to sine nx over square root of n. Okay, show that fnx is differentiable, right? Now looking at this, I can decide to differentiate this function. I know it is differentiable, but with limit zero, with limit zero. So now let me confirm that the limit is zero. Okay, that's the first thing. If I take the limit as when n tends to infinity of that sequence function given to me, which simply implies that I will take the limit as when n tends to infinity of sine nx over square root of n, and I think this should give us something of this nature: sine infinity x all over square root of infinity, and anything that divides infinity, square root of infinity is still infinite, and then by the time you divide anything here by infinity, you should know that that will give us zero. So hence this is proved. Okay, the limit for this fnx is what? Is zero. Now let's show that it is differentiable. So is it differentiable? Let's confirm. So let's confirm that it is differentiable. I'm looking at this now. So to show that it is differentiable, let's try to confirm. To show that it is differentiable, let me just asterisk here, and then I can decide to have check my details. Like that. So let's say that it is differentiable, which simply implies that, okay, we can actually take, okay, I think let's read it very well. Such that, show that fnx is differentiable with, okay, differentiable with limit zero. Okay, now let's confirm. I think that this is how it's meant to be. It's differentiable, that is d dx. Okay, since the function is in terms of x in this case, n is just a constant, so we are differentiating it with respect to n, not the constant. So the differentiability of that limit function, what would that give us? Does it converge? Show that d dx of limit of that function. So if I try to find the derivative, if I try to find the derivative of that limit function now, is it really zero? Okay, I think that's what we actually have to do. fnx is differentiable. Fnx is differentiable with limit zero. Let's confirm. Is it differentiable with limit zero? Let's confirm. The derivative of the limit here, we have it as zero, right? Which the first one, I proved the first one to be limit zero. Now, is it differentiable? Is that the differentiable of that limit? Is it, since the limit of that f of nx is zero? So is it differentiable? Let's confirm. If I differentiate a constant, what will I have? Constant. So it is differentiable. Now this is also proved. F of nx is differentiable with limit zero. So for which this fn prime of x diverges. So now that we have, but in this case now, this is with limit fn of x. But what if you try to differentiate first? Okay, let's say, okay, in this case now I want to find fn prime of x. So now let's confirm if this converges or diverges. So looking at this now, the fn prime of x is simply implies that, okay, I'm surely going to have fn prime of x means differentiate fnx, right? I think that's what this simply implies, as when n start from 1 to infinity. So if I differentiate fnx, what's fnx? Fnx is sine nx all over square root of n. So you must be familiar on how to differentiate. So we need to differentiate sine nx over root n, and that is something that is very easy. Just apply quotient rule. So in this bracket now, my quotient rule is vu prime minus uv prime all over v square, right? And I have my n start from 1 to infinity. Let this represent u. The upper part is for u and the down part is for v. So what's my u prime in this case? If I differentiate sine nx, n is a constant, right? So I have to differentiate this nx first. If I differentiate nx, like saying 2x, n is constant. If I differentiate 2x, that is 2. So if I differentiate nx first, that is n, right? So then sine automatically changes to cos after differentiating, right? Then you'll be left with just nx. So if I differentiate sine nx, I'm supposed to have n cos nx. Take for instance, if I want to differentiate sine 4x, if it's sine 4x, you have to differentiate that function first. Differentiate 4x first, that will give you 4. Then this sine, after differentiating, it comes to its cos. then you'll be left with 4x. So similarly for this also. Now this v is equal to square root of n, which is still written as n half. If I find my v prime, that should be half comes down, then you subtract 1 from the power. 1 over 2 minus 1, that should be minus half. So I believe that this should be something of this nature, 1 over 2 times this n minus half is 1 over n half, and that should be 1 over 2 times 1 over square root of n, and I have 1 over 2 root n in that case. So if I come straight to this expression here, I can go ahead and substitute. My v is root n, my u prime is n cos nx, right? Then minus u is sine nx, and then v prime, this v prime here is simply 1 over 2 root n in that case. So then divided by v square, and v square is square root of n, then you square it. You still have n star from 1 to infinity. So you need to deduce this expression here until you have the simplest answer to solve, to work with. Now I think I can actually find the LCM here in this case now. This is multiplying, this is multiplying. So then if I find the LCM of that numerator, I have 2 root n there. Then 2 root n, you have to multiply this. In this case now, I already have n root n cos nx, right? So that means 2 root n divided by 1 is still 2 root n. Then times this upper part now, I should have something of this nature. 2 root n is multiplying n root n, then cos nx. So this is what I should have in that case. Then minus, if this cancel this, I'll be left with just sine nx, right? Then I'm still having everything all divided by square cancel square root. Square cancel square root, I'm left with just n here in this case. I still have my n star from 1 to infinity. Now looking at this now, root n times root n, that is just n, right? N times n is n squared, so I'll be left with 2n squared there, then cos nx, then minus sine nx in this case, then divided by 2 root n. 2 root n is also divided by n, and that is times 1 over n. So if this multiply this, I will have something of this nature, 2n squared plus nx minus sine nx divided by, then root n times n, you know, when you have half plus 1, then that should be automatically equals to 3 over 2. That's 2 n raised to the power of 3 over 2 if this multiply this. Now looking at this now, looking at this expression here, what if we now decide to insert infinity in this case? Or is there any way this can be deduced? Now looking at this expression here now, I already have my sequence after differentiating. Okay, I have it as 2n squared plus nx minus sine nx in this case, then divided by 2 with n is power of 3. In this how it's meant to be. N 3 over 2 is this. Now if I try to look at this clearly now, this simply implies that if I split it up now, I have n start from 1 to infinity here. If I split it up, I will have 2n squared plus nx divided by 2 root n cube, then minus, I still have sine nx here, then over 2 root n cube. If these two cancel these two, and I have 2 minus 3 over 2. What is 2? What is 2 minus 3 over 2? Like if this divide this, that's indices. I have 2, I have 4 here minus 3, and I have 1 over 2 left. So looking at this expression here, only for this part, okay, 1 goes to infinity. Only for this part. Now if this divide this, I'll be left with just half, n half, right? So I'll be left with just root n cos nx, then minus sine nx over 2 root n cube. So this is what I still have here. 1 goes to infinity, right? So now looking at this is what I want to consider now. I want to consider square root of n, then cos nx, right? So I still have it together with sine nx over 2 with n raised to the power of 3. n start from 1 to infinity. So this is automatically my fn prime of x, right? Now the question says for which fn prime of x diverges. So let's show that this diverges. And if you want to show that this derivative, this fn prime of x, if you want to show that it diverges, that means you are trying to find the limits. If you try to find the limit as when n tends to infinity of that sequence of function given to us, fn prime of x. So if you notice that the result gives us infinity, it automatically diverges, then that ends the proof. So now let's confirm. If I take the limit, now if I take the limit as when n tends to infinity of this that I just got, I've created this what I have here. So in the material, I notice that they only make use of this. Okay, they only make use of this without using the other part. And I believe that this should be the derivative of that function. This should be the correct answer for that derivative of that function. But that does not mean, because under, okay, sorry, I don't need to put this again. Because under limit, I can decide to split it up. I can take this and this and this. So I want to show that it diverges, right? I want to show that it diverges, not converges. I'm very sure that if I use this one, okay, let's confirm. Now I have the limit. I can split this thing up. If you have limit of a minus b, I can split it up. It's allowed. So then I have limit as when n tends to infinity here, and I have square root of n plus nx here, right? And then I can also split it up with minus limit as when n tends to infinity of sine nx over 2 root nq. So I'm very sure that if I take this limit here, this one will converge to 0, because I'm already seeing something over infinity, right? Then this becomes 0 here. So if all this one becomes 0 now, so what happens to this one that is here? Let's check. N tends to infinity of square root of n plus nx. This is, if I substitute n to be infinity, that's square root of infinity, then cos infinity x, which is still infinity, then minus, if you find the limit of this one, all over 2 root infinity q, then n over infinity will surely give you 0 in this case. Now looking at this now, root infinity is infinity. Cos infinity will actually give you, I think that should tends to 1 or so, I can't really remember. So infinity times 1 will end up giving us infinity in this case. Everything we have here times infinity will actually give you this infinity. Then minus 0, you should be left with infinity. So this is infinite. Okay, it's infinite. Now I notice that limit as when n tends to infinity of the derivative that I just took now is equals to infinity. Since it's equals to infinity, what happens? Then it does not converge. Since it's infinite, then we say it what? Diverges. It diverges. So that's how we show the complete proof for this. Okay, where is question sef? This is it. Okay, show that fnx is differentiable. Before I do that, it's differentiable, like they said, it's differentiable with limit 0. So I have to show the limit 0. I have to show that this function fnx has a limit of 0. Then when I now take the differentiate, when I differentiate that limit 0, that means it will surely converge in that case. And I believe that, so as far as I have the limit at 0, then what happens to that function? It surely converges. So it's not a must they put it in that statement that this converges. But what I'm actually trying to, where we're actually heading to, is to show that for which this fn prime of x diverges. And to show that this diverges now, that means you need to take the limit as when n tends to infinity of this derivative sequence of function. So when you derivate that sequence of function and you notice that the result is infinite, then that means what? It diverges. So I think this is the main point that we need to prove. This is what we need to show for that. This is the major thing that we need to show in that proof, that this actually diverges. But at least you must still be able to show that this for fnx has a limit 0 and it is differentiable with that limit 0. Yes, it's differentiable, but it is not differentiable for fnx. Do you know, if I want to find the derivative now, if I now show that the derivative of the fnx which diverges, I'm not sure that the differentiability is, if you want to differentiate to infinity now, does that have any answer? It does not really. It does not really have an answer. And if being it is constant now, then we say it is equal to the constant. So, but this end, it will just end here. It diverges. So I think that's all for now for the examples I was trying to explain. So after this now, we need to move straight to the next topic, which is the uniform convergence. This is what we need. This uniform convergence appears mostly in past questions. Like you can actually see at least four. At least four. If you be given a series of functions and then you'll be asked to show that that series of function, or does it verify whether it's uniformly convergent or not? Does it converge uniformly or not? So that's how the question comes in. So for this uniform convergence, it actually has its own definition and theorem. The theorem is the Weierstrass theorem also. That's what we use most of the time. But the definition, I will have to give it to you. After the definition, I will state the definition for it, and at the same time as well state the theorem. So I think that's what we need. We need to consider these two. So if you understand these two, if you understand the definition and the theorem, forget. No matter how they give you the series of function and they ask you to show that it converges uniformly, it should be easy for you to do. That is if you understand the definition very well. So in our next video, I will state the definition, and as well I will state the theorem we are going to use. Thanks for watching.